Good day, everyone. I'm Arabela Ortega, and on behalf of my groupmates Gyan, Billedo, Federico Lazo, Robert Llaguno, and Lee Robin Villarama, we are here to present our project entitled Human Activity Recognition Using Smartphone Sensor Data. Let's start with the business understanding.
Human Activity Recognition, or HAR, is one of the most significant research areas in pervasive computing and health technology due to the availability of low-cost sensors, accelerometers, and advancements in machine learning and the Internet of Things. This is because the ability to accurately classify human activities enables a wide range of applications including health monitoring, fitness tracking, and elderly care. Smartphones equipped with built-in sensors such as accelerometers and gyroscopes offer an efficient and cost-effective platform for HAR without requiring additional wearable devices, which is why extensive research has been conducted on smartphone-based HAR over the past decade, focusing on essential steps such as data acquisition, feature extraction, and activity classification. These studies highlight that no single approach works optimally in all scenarios, emphasizing the need for models tailored to specific use cases and populations. Moreover, while research exploring the application of deep learning techniques have advanced HAR performance, challenges remain in improving generalizability, reducing computational requirements, and addressing data quality issues. These gaps highlight the need for robust classification models capable of handling diverse sensor data efficiently. So in this presentation, our team will highlight the significance of HAR for health, fitness, and smart technology, go over the key challenges and common research questions in smartphone-based HAR, and thoroughly discuss our approach to classifying activities using random forest and evaluation metrics. More specifically, our study aimed to answer three key questions. Which physical activities can be most accurately predicted using smartphone sensor data? How do sensor signals from accelerometers and gyroscopes differ across common activities? And are there any inconsistencies or anomalies in sensor readings that could affect prediction accuracy? And as mentioned earlier, we used random forest as the primary algorithm in going about our study. Performance was evaluated using accuracy, precision, recall, and F1 score to ensure reliable predictions.
So here we have data understanding. So the data economy is rapidly evolving, driven by several key factors that shape its growth and impact. Understanding these drivers helps to appreciate how data is transforming industries and influencing economic strategies. So here are the primary forces behind the rise of the data economy. So these are the technological advancements, increased data generation, data monetization opportunities, enhanced decision making, and as well as regulatory and ethical considerations. So here in data understanding, we have the HAR dataset overview or the human activity recognition overview. So we have the participants, we have ages 19 to 48, in which there is a device worn on their waist. So the activities would be walking upstairs and downstairs, sitting, as well as standing and laying down. So the sensor data, which is a triaxial acceleration, which involves the body plus the gravity, and the triaxial angular velocity. So the sampling rate would be 50 Hz. The segmentation would be 2.56 windows, 128 samples. So next, we have the signal processing and feature extraction. So the pre-processing steps would be median plus low pass filters, which is about 20 Hz and 0.3 Hz. So signal decomposition would be body versus gravity, and the derived signals would be jerk, angular acceleration, and signals magnitude. So the feature set would be equal to 561 in total. So the time domain would be mean, standard deviation, jerk, and correlation. The frequency domain would be energy, skewness, and kurtosis. The geometric would be angles between the vectors. Then the transforms would be FFT for frequency features. Now for the data splitting and statistical summary, we have this 70% training and the 30% testing. So here we have the 2,947 windows in test. So all 6 activities are well presented. No missing values, features show appropriate variance, mix of normal, skewed, and multimodal distribution, in which informs the need for scaling and normalization. So the key insights and takeaways would be well-prepared dataset for supervised learning dynamic activities, which would be easier to clarify, such as the clear sensor patterns. So for static activities, we have the sitting/standing for an example, and there are more challenges due to overlaps. Smartphone sensors are a viable alternative to wearables, as well as ready for modeling stage with strong generalizing potentials.
The data preparation process ensured that our dataset was clean, consistent, and ready for modeling. I'll be discussing the procedures we followed to transform raw sensor data into a well-structured dataset suitable for effective model training. The process involved 5 key steps. Step 1, data loading. Step 2, feature naming and merging. Step 3, mapping activity levels. Step 4, feature selection. And finally, Step 5, train test split. In data loading, training, we imported key Python libraries like pandas, numpy, matplotlib, seaborn, and scikit-learn. Then loaded the metadata files, features.txt, which holds 561 sensor feature names, and activity labels.txt, which maps numeric codes to activity names. Next, we imported the core dataset files xtrain, xtest, ytrain, ytest, subject train.txt, and subject test.txt for the participant IDs. All files were read into pandas data frames using whitespace delimiters to preserve the original structure. For step 2 feature naming and merging, we name the feature contains using the features.txt file and label the subject and activity columns. We then combine the training and test sets into one complete datasets using pdconcat. After merging, we check for duplicates and apply drop duplicates just to be safe. This gave us a clean dataset with 10,299 rows and 563 columns. For step 3, mapping activity labels, we made the activity labels easier to understand by replacing numeric codes with descriptive names like walking or standing. We used the map function and the mapping from activity labels txt to this. This helped make this dataset more readable and interpretable for both humans and machine learning models. In step 4, feature selection, we reduced dimensionality by selecting only the features related to the mean and standard deviation. We use a regular expression to filter this from the 561 original features. Then we combine the selected features with the subject and activity columns to form a clean dataset ready for classification. For the final step, train test split, we normalize the selected features using standard scalar to ensure consistent scale. We then split the data into 70% training and 30% testing using train test split, which clarify ensuring each activity was fairly represented. This gave us a clean and standardized dataset ready for model building.
Now for the modeling. In this phase, we aim to build a robust model that could classify human activities based on smartphone sensor data. Since it's a multi-class problem with high-dimensional normalized features, we chose random forest. It handles complex data well, avoids overfitting through ensemble learning, and gives feature importance scores for easy interpretation. For training, we split the dataset into a 70-30 ratio using stratified sampling to keep class balance. We reduced the 561 features to 66, focusing on mean and standard deviation, and applied z-score for normalization for consistent scaling. The random forest was then trained using 100 decision trees and a fixed seed, allowing it to generalize well across all 6 activity classes.
Now, when evaluated on the test set, our model achieved a high accuracy of 97.51%. We also saw strong performance in precision, recall, and F1 score metrics. The confusion matrix shows that dynamic activities like walking and walking upstairs were classified very accurately, while minor confusion occurred between similar static activities like standing and sitting, which is understandable given their similar sensor patterns. Finally, we looked at feature importance scores from the random forest. Features like T-gravity act mean X and F-body act jerk mean X contributed most to the model's decisions, showing the importance of both time and frequency domain signals. While the model performed well, we plan to explore further improvements such as hyperparameter tuning or applying PCA to reduce computation without sacrificing accuracy.
Evaluation. Our primary objective was to build a robust classifier using smartphone sensor data. On this first slide, you can see our key findings regarding the model's performance. We achieved a high overall accuracy of 97.51% on our test set using random forest classifier. This indicates that our model is highly effective at distinguishing between the different human activities. Looking at the classification report, you'll notice strong performance across all metrics, precision, recall, and F1 score for most activity labels. This demonstrates the model reliability in correctly identifying each activity type, minimizing both false and positives and false negatives. Moving on to our activity classification insights, this slide presents the confusion matrix, which offers a more detailed view of how accurately each activity was classified and where any misclassifications occurred. As you can see from the matrix, our model consistently and accurately separated dynamic activities like walking and walking upstairs. The high numbers along the diagonal of these activities confirm their distinct sensor patterns. However, we observed some expected confusions between static activities, particularly standing and sitting. This is a common challenge in HAR, as the sensor signals for these activities can be very similar. Despite this, the misclassification rates are low, demonstrating the model's overall strength even in these challenging scenarios. This slide highlights the important features that contributed most significantly to our random forest model's decisions. Understanding feature importance helps us grasp which sensor signals are most crucial for activity recognition. The bar chart showing the top 10 important features in random forest reveals the variables such as T-gravity act mean X and F-body act mean X were among the top contributors. This finding underscores the importance of both time domain and frequency domain signals derived from the accelerometer and gyroscope data. It indicates that the model heavily relies on how gravity influences the body acceleration and the rate change of the body acceleration, providing valuable insights into the underlying movement patterns. Finally, let's discuss our plan for future work. While our model demonstrated strong general performance, there's always room for further optimization and improvement. Our next steps includes exploring hyperparameter tuning to fine-tune the random forest classifier's parameters. This process will systemically search for the optimal settings that could potentially yield even higher accuracy and efficiency. Additionally, we plan to investigate dimensionality reduction techniques. Reducing the number of features could not only enhance computational efficiency, making the model faster to train and deploy, but also potentially improve its accuracy by removing noise or redundant information. This will be crucial for potential real-world applications where computational resources might be limited.
And that is all for our presentation. Thank you for watching.